And so sometimes we hold a topical class, which next week will be one, but you'll need your Bibles if you want it, on the Dead Sea Scrolls. Last week, I can't remember what I did. Angels, devils, and demons. That was half biblical, half topical. This week, we have a guest speaker. And like next week will be Dead Sea Scrolls. And the following week will be an absolute Bible study on eternal life as we look at the last 4 chapters of the book of Revelation. Now, I got to do some bouncing to get there, but we will. But it is a pleasure to welcome all of you today. And let's begin with a word of prayer. Gracious and loving God, we give you thanks that we can come together in your name openly to study our world, to fellowship with one another, to grow in our faith and in our knowledge, and to acknowledge you as the Lord of the universe. So bless us and guide us as we look at our today's subject, that we might go forth and have more things to discuss and more things to share. In Christ's name we pray. Amen.
Amen.
Before I introduce Bob, just a word here about my physics journey. And Lee's here too as a chemist, and that relates to my physics journey. In high school, I carried a very high grade point average. So I got to my senior year, and the choice was you could take physics or you could take typing. Now, in my great foreknowledge of what was coming in the computer age and the need to type, I decided an A in typing would be much better than a B in physics because I'd already had a B in chemistry, and I didn't think I could improve upon that. But I've learned and become interested in a number of things that have to do with physics since then, but it doesn't begin to compare to what you're going to hear today. I'll be introducing Bob Miller, who is a 13-year veteran of this congregation. I got him by 2 years, but Bob's been here for 13 years. And Bob has a bachelor's degree in physics from Penn State University. Any Nittany Lions here? Yeah, I got a couple of them. And has a master's degree in physics from Fairleigh Dickinson, which is a school in New Jersey, right? New Jersey. New Jersey is a strange college setup. None of them are named New Jersey State. I mean, Rutgers is the state university of New Jersey, I guess. But he has that, as well as a master's degree in electrical engineering. And he worked for 38 years for the Army Research Laboratory. And while doing that toward the end, he also taught at several community colleges in New Jersey, and then they moved to the villages, and he taught for several years at Lake Sumter Community College in Leesburg on the very subject that you're going to hear today, which is climate change. And we'll turn it over to Bob. It's all yours.
Thank you.
I'm going to close this door.
Okay. I want to start by explaining the difference between weather and climate. Weather is what happens in a particular place at a particular time. Climate is an average over long periods of time and maybe large areas as big as the whole world. And our subject is climate change. However, I'm going to begin by talking about weather. In the 1960s, meteorologists felt that if they had a finer grid of weather stations collecting data, and they were starting to use computers to analyze this data, that they could improve upon their forecasts. One of these was Dr. Edward Lorenz at MIT. And he was studying a particular model of weather. If you have a hot spot on the Earth, say a lake that has received sunlight all day and is warmer than the rest of the surrounding area, you'll get a column of air rising off of that hot spot. But then as it rises, it cools and it'll come down the outside. And you get these circular modules that carry out this convection process. There's a set of differential equations, nonlinear differential equations, that describe what's happening here. And Dr. Lorenz was working with his computer and these equations and coming up with what looked like weather. Those around him who saw what he was doing agreed that it looked like weather. Well, at one point he wanted to rerun a particular section of the program. So he took the parameters that he had. One of them was 0.506127. But what he entered into the program was 0.506. He left off the last three digits. And when he ran it, it started out looking like what he had done before. But as time progressed, it started to come apart right in here. And then pretty soon, one didn't look anything like the other one. He didn't blame the computer. He went into the research of it and found out that what he was faced with was a sensitive dependence on initial conditions, which is the basis of chaos theory. We're going to take a look at what he had here. We'll give this a minute. This figure is called the Lorentz attractor. Mathematicians, come on. Here we are. Okay, where's my cursor? It's hard to see in the black. Here we go. Mathematicians had been studying these things they called strange attractors for 100 or more years. And the results of Lorentz's equations gave us a strange attractor. And a couple of things happened here. You see, this thing it reminded people of a butterfly. And it became known as the butterfly effect. The idea of the butterfly effect is that the initial conditions can be varied very slightly. If a butterfly flaps its wings in Beijing, it can affect storm systems in New York 3 weeks later. And, well, that's what we're looking at here. If you follow the end of, let me find it, there it goes. See, it goes around that loop a couple of times, and then it will go around this loop a couple of times, and it seems almost random. and it never retraces the same path. It's a fractal, and or a strange attractor. When that point is going around one of the loops, you can make predictions for a fair amount of time. But when it's heading toward that middle section, all bets are off. There's no guessing which way it's going to go. So, okay, some features of weather, these convection cells, for instance, can be chaotic. Chaos is defined by sensitive dependence on initial conditions. And in some regions, prediction is possible, but there are places where it isn't. In physical systems like this one, there seems to be a threshold of energy below which it's not chaotic, but above a certain energy level, it becomes chaotic. I brought this up to make the point that weather is complicated stuff. And the average of weather over time in large areas, climate, is also complicated. Okay, let's talk about the energy for a minute. Energy comes in various forms. Kinetic energy, the energy of motion. Potential energy, the energy stored as an object is raised off the ground. Electrical, and most important, sunlight or light energy. And light energy through photosynthesis in cells gets converted into chemically stored energy, like sugar. Energy is the ability to do work. But energy eventually ends up as thermal energy, temperature. But under normal conditions, energy is not created or destroyed. If we receive energy, we have to get rid of energy. The only exception is that in a nuclear reaction, mass can be converted into energy and energy can be converted into mass, but that's not what's happening in our atmosphere. Okay, here's the energy balance equation for a planet in general. You have the solar radiation that is hitting that object, that planet. Now, this alpha is reflectivity. So on Earth here, things like snow, clouds, that sort of thing reflect a lot of the sun energy. And so it reduces what we are actually receiving. On the other side, the Earth gives off energy. Because of our temperature, we give off energy in the infrared region of the spectrum, back into space. And if this doesn't balance, if the energy in is different from the energy out, something has to change, and that change is temperature. It's the only thing left. Okay, now, that temperature is measured on the Kelvin scale, the absolute zero scale. It's the only one that makes sense. I have a figure down here. 0 degrees Kelvin is minus 273 degrees Celsius. We are about 15 degrees Celsius as an overall average of the world. So we're about 288 degrees here. We emit our radiation based on that temperature. I multiplied it by 1.6 because I read some time ago that since the beginning of the Industrial Revolution, our temperature has gone up about 1.6 degrees. And that's just over 0.5%. We're talking about very small changes over long periods of time. But these changes turn out to be important. Here is some data. The red curve is temperature. The blue curve is carbon dioxide. And you see they show a great deal of correlation. This goes back 400,000 years. This data came from ice cores on Antarctica. They have a hollow drill. They drill down and then pull out this core of ice. And then they measure the layers. And the carbon dioxide is measured directly because air bubbles get trapped in the snow as it lands and then compressed into the ice. And so tiny air bubbles release the air, and the carbon dioxide content can be measured with a mass spectrometer. Here's the temperature data. You might wonder who was standing around with a thermometer 400,000 years ago. Of course, the answer is nobody. The temperature data comes from pollen. Pollen gets distributed worldwide by the winds. And in these layers in the ice core, they can measure the ratio between tropical plant pollen and deciduous plant pollen. And it gives them a pretty accurate measurement of the temperature at that point in time. Now, you can see they move up and down pretty regularly. This is a natural phenomenon. It's based on the Earth's orbit around the sun, the tilt of the Earth, the nutation of the Earth. A rotating body wobbles. And those things have a cycle. They come back to the same point every 100,000 years approximately. And that cycle is what we see as the cycle between warming periods and ice ages. However, where we are now with the carbon dioxide, we're over 400 parts per million. That is higher than we have ever been in the entire history of humanity. That's the scary point of this plot.
How does that affect us?
We're getting to that. Okay. Now, we saw a strong correlation between temperature and carbon dioxide in that last graph. Correlation does not necessarily mean cause and effect. We have to look deeper to find that. Well, here it is. This curve, the red, represents the incoming energy from the sun as a function of wavelength. And visible is right there at the peak of that. Green would be at the peak. And that is a function of the surface temperature of the sun. That's what determines how much energy the sun is putting out. What happens here on Earth is represented in the blue curves over here. They're in the infrared region. And what you will see in there, you see this gap right in here near the peak of, we have different curves depending on different areas being at different temperatures. But here near the peak is where carbon dioxide has a strong absorption band. Carbon dioxide is absorbing some of that heat that the Earth is trying to get rid of. I'm going to talk about water vapor next, and then we will mention methane a little later on. But carbon dioxide seems to be the culprit in what's going on here. Water vapor is also a greenhouse gas. You could see that in the chart there. But the effects of water are ambivalent because not all of the water is in the atmosphere as vapor. Much of it is up there as water droplets or ice crystals, which form clouds. And clouds are highly reflective. So they're part of that alpha from that energy balance slide, reflecting energy away from us. But the vapor will also absorb some of the infrared we're trying to get rid of, but we can't do anything about it since we can't live without it. So water we have to accept for what it is. Here's a shorter graph of temperature. And in 1999, Michael Mann published this curve and got into trouble with everybody. Nobody believed him. They all tried to prove him wrong. Well, 78 researchers from 24 countries and with many other people were working on a project and reconstructing Mann's curve for over a period of, I forget how many years. Now they took their data not just from the ice cores. They got it from tree rings, corals, stalagmites, pollen, historical documents, and measurements. The red here is when we finally had thermometers and were able to actually measure this stuff. But you can see our temperature here shows from about -4 to right now about +0.2, -0.4 to 0.2 degrees Celsius rise in that time. It doesn't sound like much. It's not happening real fast. But we're going to look at how important it is. Methane, CH4. On a molecule-to-molecule basis, CH4 absorbs about 70 times, and recently I read something that said like 84 times as much infrared energy as a CO2 does. However, CO2 is in our atmosphere at a level of about 400 parts per million. And we measure methane in our atmosphere in parts per billion. So its effect is much lower because there's a lot less of it. Carbon dioxide is very stable. A carbon dioxide molecule in the, put into the air now will probably still be here in about 100 years. A methane molecule has a lifetime of about 5 years in the atmosphere. But what happens to it is most of it disappears by being oxidized, which produces more carbon dioxide. About 300 million years ago, plants developed the ability to produce cellulose and lignin. These are polymers of sugar molecules. And these are the structural materials that plants use to build stems, leaves, roots, trunks. And at that time, plant life went wild. You know, plants take in carbon dioxide and give off oxygen. Well, the oxygen content at that time went to about 35%. for about the last million years, it's been 21%, which is comfortable for us. Now this biomass eventually died off, got covered over, as happens on land, and in the temperature and pressure conditions in the Earth's crust turned into coal and oil and methane and things that we pump up and burn now. More recent history. This happened in the 1700s, late 1700s. Newcomen developed a steam engine. It was called an atmospheric steam engine, and it was used for pumping water out of mines. Now, before this, people were using coal where they could find it. They didn't find a lot of it. One of the places was along a beach where the water, the ocean, had eroded away a cliff and uncovered a seam of coal. They called it sea coal. And they would use it to heat their houses and that sort of thing. When they had the Newcomen engine pumping water out of mines, they could go below the water table, find more coal, and the availability of it encouraged the use of it. Then Watt came along and improved on Newcomen's engine. And if you look at old factories, I love going around and looking at historical buildings like that. But a lot of them, if it was a factory, was built next to a river. And the reason was water power could operate the tools of the factory. Well, once you had a steam engine, you could build your factory anywhere you wanted. And here's an early steam locomotive. Now, the first ones of these were used at the coal mines. And they would, at first they used wooden rails, but wooden rails didn't last very long with the loads they were putting on them. And so they eventually went to iron rails. But they would use this to cart coal from the mine to a waterway where they could put it on barges and distribute it where it was needed. Well then, with available coal, the Bessemer process was developed for refining iron and steel. And also, coal was used in cement plants. Well, iron, steel, cement, these are the basis for the Industrial Revolution. This is the infrastructure of the bridges and roads and tall buildings and that sort of thing. And that's what came out of our discovery of the availability of coal, cheap energy. Here's a steam-powered farm tractor. So the steam became a mobile power source. And then here is Pennsylvania's first oil well. So oil then added. Before that, people were using whale oil and that sort of thing to light their homes. And now we had kerosene, which was a lot cheaper and more efficient. Okay. Here's the carbon cycle I learned about in 8th grade. Very simple. Plants, through photosynthesis, give off oxygen. The animals and plants breathe in oxygen and give off carbon dioxide. That's the cycle. This is even missing the other half of that cycle, because in photosynthesis, the plants are creating sugar, which I mentioned before is stored energy. The animals eat the plants, the products of the plants, and give off carbon dioxide. So it's a two-direction cycle. Now, here's a more realistic version of the carbon cycle today. The right-hand side of it is what we consider the natural part of the cycle. The plants producing oxygen, absorbing carbon dioxide, but methane is coming from dead organic material. The left side of the curve is more of the industrial part of the carbon cycle. And we look at factories giving off emissions, transportation, agricultural, procedures that absorb or emit carbon dioxide. And one of the places that carbon dioxide goes when we put it into our atmosphere is into the oceans. Now, when I first heard about it, I said, oh, good, that'll buffer the effects of the carbon dioxide. And then I read some more articles and I said, oh, not so good, because carbon dioxide in water is carbonic acid. Carbonic acid is a weak acid. It's seltzer water. But our mollusks don't like it because their shells are soluble in carbonic acid. And the small baby mollusks have trouble growing. They get eaten before they can grow a shell to protect themselves. And I don't know, I happen to like clams and oysters and that sort of thing. I'd like to keep them around. Now, one thing I want to point out here, we give off our gaseous waste materials from everything we do. When we exhale, we're exhaling carbon dioxide. When we burn coal, we're putting out carbon dioxide. And the wind carries it away and we never see it again. That doesn't mean we can forget about it. I want to give you a mental image of the extent of our atmosphere. If you want a mental picture of how much atmosphere we have, think of a coat of paint on a basketball. That's it. We can't waste it. Okay, consequences. I mentioned the 1.6 degrees. I did a calculation a few years ago of how much energy 1.6 degrees in our atmosphere would total. And I came up with almost 10 to the 20th joules. That's a 1 with 20 zeros behind it. Now, a joule isn't a very big unit of energy, but that's an awful lot of them. What is our atmosphere going to do with that extra energy? It's going to produce stronger storms. Higher temperature air, even up 1.6 degrees, can hold more moisture than colder air does. And so the effect that this has is in traditionally dry areas where the geometry of mountains and location of oceans and that sort of thing causes an area to be drought prone. It'll be even drier because the air, the atmosphere, is able to hold on to its moisture instead of dropping it there. And then in traditionally wet areas where the mountains cause temperature changes that cause rainfall and that sort of thing, we get flooding, where those areas now get more rain than they used to. We're seeing that. I mean, that could be California. And this could be the Northeast. The other problem we have with this is this has been measured. The season and the territory of disease-causing insects is expanding. They're there for longer times, and they're covering more area. So you take malaria, encephalitis, Zika, all of those things that are carried by mosquitoes. It's expanding. And then you take the Lyme disease. I just read that Maine this summer had its first 2 cases of Lyme disease. I read another article that somewhere in Ohio, and I don't remember the name of the disease, but they had their, it's a mosquito-borne disease, and they had their first cases of that in Ohio this year. So we know that's happening. Sea level rise is another consequence. We were at dinner with friends a few weeks back, and somebody asked me something, and I mentioned climate change, and I wasn't with people who were always in agreement with me on that. And one of the fellows says, "What's wrong with going up a couple of degrees? That sounds good to me." And I started to tell him about some of the consequences, and I mentioned that if we lost the Larsen ice shelf in Antarctica, the ocean could rise 30 feet. My house here in the village is at 28 feet. Now this won't happen tomorrow, but by the end of the century we may see something like this. And I won't see it, but I have children and grandchildren and great-grandchildren, and they will. Well, anyhow, one of the fellows there said, 30 feet, that's crazy. I didn't argue with him. I went home, and I looked up on the internet a NASA report that said if Antarctica melted, the sea level could go up almost 70 meters. That's 200 feet. I don't expect all of Antarctica to melt, but the potential is there, and it's real, and it's happening. Sea level is rising. Okay, it's risen, maybe 0.2 of a meter so far, a little over that. But the projections are, the red one is if we don't do anything about carbon dioxide. The blue one is if we take too long in doing things like this can happen. What's going to happen to Miami, Louisiana, New York? The other interesting thing, that 30-foot figure. I read a statistic years ago that the land area within 30 feet of current sea level it represents about 3% of the land area on Earth and contains 10% of the population. When those people have to move, it's going to be a hassle. We're not talking about big changes, but important ones. Changing weather patterns. Flooding in some areas, drought, and fires in other areas. The expanded areas for insects, mosquitoes and ticks in particular. I did the other calculation. 10 to the 20th joules is 278 trillion kilowatt hours. When you pay your electric bill, you pay for kilowatt hours. That's a unit of energy. A power level times the time you use it is energy. And that's quite a bit of energy, additional energy in our atmosphere. Most common misconception, I've heard this so many times. Somebody says, oh, we're not warming, look at last winter. A cold winter does not contradict climate change, global warming. What happens is this. We are being told that the Arctic is warming twice as fast as the rest of the world. And I have a reason for that I'll get to too. Now that means that the temperature difference between the North Pole and the northern latitudes is decreasing. Temperature difference is what produces wind. And if you've heard of the polar vortex, that is a circulation of wind around the North Pole. That polar vortex tends to contain the coldest air at the North Pole. That polar vortex is getting weaker. And as it does, more of the cold air comes down from the North Pole into the upper latitudes of Europe and Asia and America. Okay, here are things we see happening. Arctic sea ice. That was the picture from space in 1984. And this is from 2012. Now, what that means is that this area, and we're talking about over 1 million square kilometers, 3 million square kilometers of ocean was covered by ice and snow. And it was part of that alpha, that reflectance that was in the balance equation. It was reflecting sunlight back out, reducing our temperature. But now, that area is open sea, blue ocean that's absorbing that sunlight. That's one of the reasons that it's warming faster up there. Antarctica is losing ice. Last year, a piece of the ice shelf the size of Delaware broke off and floated out into the ocean. Now that did not affect sea level rise because that ice was already floating on top. It was displacing its weight in the water. So it didn't change sea level. But it was a buffer holding the ice on land where it is. And that ice is sliding now. And sea level rise is going to accelerate. It's been going very slowly over hundreds of years. But now we see acceleration happening. The same thing is true on land. The tundra, northern areas that used to be snow-covered year-round, were reflecting almost all of their sunlight back out into space. But now that brown dirt is absorbing a lot of that sunlight. So these are feedback phenomena. And here's the other one, the heat content of the ocean. And they're talking in units of 10 to the 22nd joules. And you can see the rise it's taking up to recent years.
How does that affect the life in the ocean?
Can we save the questions till the end? I'm almost finished. Okay, I'm changing topics now. I want to talk about who do we believe. I hear people saying, oh, well, the scientists don't even agree on it yet. Well, controversy is part of science, an integral part of science. We need it. Discovery fuels scientific advancement, but controversy keeps it on track. And I don't know if any of you remember reading about cold fusion, where some laboratory presented a paper where they, in a solution on a lab bench at basically room temperature, got more energy out than they got in. And they attributed it to fusion taking place in this liquid. Well, I know the laboratory that I work for started experiments in that direction. Because if somebody else can't confirm a result like that, we have to go back and look at where it came from or how it happened. And so many laboratories around the world tried to reproduce cold fusion, and nobody could. So we went back and found out what they were really measuring that made them think it was fusion that was happening. Technical societies have committees that pass on papers that are submitted for publication or presentation at a conference. I know I was part of that. I spent 25 years in the development of flat panel displays. And I was a member of the SID, the Society for Information Display. And I was on the papers committee. And before our big conference every year, we would receive potential presentations. We would send them out to people who were working in the same field, who knew what was going on in that field, to evaluate them. And mostly they would come back with comments like, this equation needs further verification, or we need more data, things like that. It wasn't based on whether or not we disagreed. I disagreed with one of the fellows there in what he was doing, but I accepted his papers and gave him the chance to explain what he was doing. That's how it works. It's that kind of disagreement that keeps science on track. Approval is based on the quality of work, not on your opinion. At least we hope that's how it works. But that's why you have multiple people in a committee like that, so you get a collection of opinions. Oops. Okay. The statistics are that among climate scientists, 97% of them agree with what's happening, how it's happening, what's causing it. So that my first comic strip slide mentioned a debate. There is no debate. 97-3 does not amount to a debate. And let me explain a little further. What we know about most of that 3% is that they come from reputable institutions, but they are funded by these institutes with fancy sounding names. Americans for Prosperity, who can argue with that? Well, they have a different take on it than I do. And what we're seeing here is our 3%. They mostly bypass the peer review process. They're not submitting papers, very few, submitting papers to journals and scientific meetings. They write articles for the newspaper and magazines. They go on television. They write books. And they are being funded by these institutes which get their funding from the Koch brothers, whose vast fortune is based on coal, from the oil companies. I recently read that Mobil Exxon has stopped funding these organizations. Well, that's an admission that they were funding these organizations. And beyond that, I have to wonder, did they really stop funding them? Or did they find more clandestine ways of doing it? So it's still a question as far as I'm concerned. Last slide. There's hope. Solar energy with some subsidization is close to being competitive with fossil fuel energy. And things are changing. Things are still changing. The way to make solar energy truly competitive is either lower the price or increase the efficiency. Well, both things are happening. The price has already come down considerably for solar panels. But if you take a silicon solar panel and add a perovskite layer on top, the silicon absorbs and converts sunlight into electrical energy in the short wavelength end of the spectrum, the blue-green end of the spectrum. But perovskite converts the long wavelengths and is transparent to the short wavelengths. So the short wavelengths get through the perovskite to the silicon, but the long wavelengths get absorbed in the perovskite, producing more energy. I've seen figures of from 18%, which is a typical rooftop solar panel, up to 22%. Well, that's a significant improvement in efficiency. Wind is already competitive with coal in cost. The downside of both of these is that the sun doesn't shine all the time and the wind doesn't blow all the time. So what we need is storage. Now here is a picture of a flow battery installation that could be built next to a solar farm like this. And it would store energy during the day and provide it to the grid at night. And the same thing is true with wind. Here's a diagram of that flow battery where the electrolyte is being pumped around the system and refreshed before it's brought back in to operate the storage in the battery. And the last thing I have here is nuclear power. People get all nervous when they hear nuclear. But there is a safe nuclear power. This kind of reactor, which is called a molten salt reactor, was built at Oak Ridge National Laboratory in the 60s. The reason we don't have molten salt reactors online today is because it didn't produce plutonium to build our bombs with. And so politically it was decided we're going to go with the, now, in a high pressure water reactor, the water tank holding the stuff that's being circulated goes to 1,600 pounds per square inch. If something's going to pop, that'll be it. This basically works at atmospheric pressure. And it's safe because it's built over a chamber. And in the bottom of the reactor is a thermal plug. And if this reactor starts to run away, the temperature will melt that plug, drop into the chamber, stop the reaction or slow it down without any human intervention. And we can have safe nuclear power. And nuclear power doesn't produce any carbon dioxide. But from what I've read, to get through the regulatory process, to get the laws changed to accept this, would take us 15 years. I don't know that we have 15 years. The other thing that is happening is, these are mostly experimental yet, but people have been working with carbon dioxide absorbing minerals. And many natural minerals absorb carbon dioxide. A lot of the stuff that's being made to do this involve expensive metals, platinum and that sort of thing. But people are finding less expensive ways of building minerals that will absorb carbon dioxide. So carbon capture is a real possibility. And now I'd like to open for questions.
I've got a microphone so everybody can hear. There were questions back here somewhere. Don.
Bob, what about LED versus incandescent lighting? Do you have any figures on that, whether it's making an effect?
Yeah, I've had to skip some things. I put a semester's worth of topics in an hour here. So, yeah, that is a great step forward. An incandescent bulb consumes about, no wait, let me get it straight. Produces about 18 lumens per watt. Fluorescents produce about 80 lumens per watt. There's a big step forward right there. LEDs are all over the place, but they can produce hundreds of lumens per watt. And now we have the crystalline LEDs that are available in lighting fixtures. You can go to Home Depot or any place like that and buy them right now. Coming online are organic LED light emitters, which you could coat your whole ceiling with and have soft light, no shadows, in any color that you want. So a lot is happening in that direction. Oh, I don't have my phone. I didn't pick it up. I was going to show you an organic LED display. So that's something that's really happening.
Other questions?
Yes.
Okay, Lee.
Is cold fusion still continuing? I mean, are people still looking at cold
Fusion, not cold fusion. People have studied the tokamak reactor for 50 years. And after 50 years, we still haven't been able to create sustained fusion reactions in the magnetically confined gases in a tokamak. What else is being studied is laser fusion. California, the national lab, which one? Anyhow, they've built a laser fusion reactor where they drop a pellet coated with a dense material but containing lots of hydrogen and particularly deuterium, H.2, inside. And then they hit it simultaneously from all sides with a laser beam. And that causes the outer material to blow off, compressing the inner material, and they have gotten more energy out than the lasers put in some experiments. But that isn't the total energy that was put in. A lot went into that beforehand. So it's not to the point where it's being economical yet. But the line I always liked was fusion is the energy source of the future and always will be.
Anything else?
Yes.
Kathy.
I just wondered if you had some practical ideas of what we as individuals can do to help with this.
For myself, for the past 10 years, I've been driving a car that gets from the high 40s to the low 50s in miles per gallon. And it's a comfortable car and very practical for me. I also have a set of solar panels on my roof. Now, I am subsidizing those solar panels. The total of what I'm paying for the panels, plus my electric bill, which is very reasonable, but it adds up to more than what my electric bill would be. But I'm willing to do that. I can pay a few cents more for my electricity and still eat. Yes.
I have a practical question about solar panels. We also have extensive solar panels on the roof of our barn. And,
Okay.
and when we first put them up, of course, they were very expensive. When we first put them up, we saw enough of a return that we were happy that we did it. And over time, the solar panels get dirty and don't absorb the sunlight the way they did in the beginning. And we're having problems keeping them clean because they're on the roof of a barn and we don't want to be up there.
Right, I agree.
So
How
do you
long
have-
how
do you-
long have they been there?
It's probably 7 or 8 years now.
Okay.
Do
Yeah.
you have any any advice or solution for something like that?
Get somebody with a cherry picker to get up there and
Right.
that's the best advice I have. My daughter put solar panels on her house before I did. And she's up in upstate New York. And one day I was talking to her on the phone and I said, "How are your solar panels working?" She said, "They aren't." I said, "They aren't? Why not?" She said, "They're covered with snow." But she's very happy with them overall.
Anyone else?
Okay, thank you.
I just want to thank Bob for being with us and sharing. We have a lot of expertise within the congregation. It's a matter of putting our finger on it. That's one item. The second item is if you have any subjects that you'd like to talk about or think we can, biblically, topically, or something like the Big Bang Theory that Lee has done for us, we can do it. And let's see, I know we have some members of the committee here. Who's member of the Education Committee? Raise your hands. Okay, we got 4, 5. Just mention it to them. We'll probably meet sometime in October. We don't have the second semester set up yet. And so if you talk to me, talk to Bruce Dillman, who works equally with me, putting this together, we'll see what we can do. But all I can say is that I know what's going to happen next week if I get home and get more busy. I've been working on, I've done a lot on the Dead Sea Scrolls. Some of you have had an extensive class with me under Dead Sea Scrolls, but I'm trying to zero in on the Dead Sea Scrolls and Jesus. What's the relationship? And we will give you some background on the Dead Sea Scrolls and then background on the New Aramaic findings as well as the New Testament input into the Dead Sea Scrolls. So with that, we say, go in peace and serve the Lord, and thank you.